Good afternoon, good morning, good evening, depending on where you are located. And thank you for joining us for this new webinar offered by HESI's Environmental Epidemiology Committee. I just want to say a word about the committee to provide some context to this series of presentations. So the mission of the Environmental Epidemiology Committee is to increase the impact of environmental epidemiology in quantitative human health risk assessment and regulatory decision making. The committee is currently working on different parallel projects to fulfill this mission. And by the way, you should feel free to reach out to me if you want to learn more about what we're doing with this group. But with this webinar series, we wanted to touch on various issues relevant to this mission, whether it be through the presentation of case studies or the introduction of work being done in this space, or even more technical and methodology-oriented talks. So if you have any suggestions about speakers that you think we should invite or subjects you think we should touch on, please do not hesitate to reach out to me. So today's presentation will be focused on the replication crisis and how it impacts environmental epidemiology. But before we begin, I want to cover a few logistics. So let's see if I can switch my slide here. So this webinar is being recorded and it will be posted to HESI's Environmental Epidemiology Committee website, which is on the HESI website. You can see the link here, hesiglobal.org. Throughout the presentation, please enter your questions in the question box, and your questions will be read at the end of the presentation. If you have any question about HESI or about the activities of the Environmental Epidemiology Committee, please contact me. You can see my email address here. And finally, information about future webinars will be posted on our committee webpage. And some of you may also have heard of those webinars through HESI's newsletter, Insights. We also post on social media, so we're trying to get the word out as best as we can. I also have a brief disclaimer, so you know that the views expressed by speakers on these webinars are the views of these speakers only, and not necessarily the views of HESI or its members. So today, it's my great pleasure to introduce our speaker, Dr. Scott Bartell. Dr. Bartell is Professor of Environmental and Occupational Health and Statistics at the University of California, Irvine. His research interest is environmental health methodology with applications in environmental epidemiology, exposure science, and risk assessment. Since 2006, much of Dr. Bartell's research has focused on per- and polyfluoroalkyl substances, including linkage of fate and transport models and a pharmacokinetic model for exposure reconstruction and epidemiological analysis in the CA studies, development of Bayesian statistical methods for biomarker-based pharmacokinetic calibration in exposure reconstruction, and assessment of the potential impacts of exposure measurement error on previous epidemiological findings for PFAS. Dr. Bartell currently serves as principal investigator for the UCI PFAS health study, which is a California site in the CDC-ATSDR multi-site PFAS study. Today, Dr. Bartell is going to present some of his thoughts to help us better understand the replication crisis and its implication for environmental epidemiology. Dr. Bartell, welcome. We are very happy to have you. And with that, I will give you the floor.
Thank you so much for the invitation to speak today. I think I need an invitation to share my slides still, which I don't see on my screen. So we'll see. Here we go. Okay, I now have the invitation. So I'm going to put my slides up. And hopefully everybody can see those now.
Yes, we can.
Okay, thank you. So, all right, there we go. So, oh, sorry, I'm trying to get my slides. There we go. Okay. So this is a topic that's very close to my heart. I do a lot of work at the intersection of statistics and environmental epidemiology. And so thinking about the statistical reliability of research findings is something I do quite a bit. And so I have some thoughts to share on this topic. If you've been paying attention in the last decade or so, either to science journals or to the popular press, you've probably seen headlines like this. Over half of psychology studies fail reproducibility test in Nature News in 2015. Or in the popular press, in The Economist, trouble at the lab, unreliable research in 2013. Cancer research is broken in Slate. And also this kind of news is also appearing in trade publications, in business journals and newsletters as well. For example, SciBX in 2011 reported that venture capitalists believe that the majority of published studies do not have valid findings, even for top journals. And then one more example, 2016, The Week, Big Science is broken. So what's going on here? Before we jump into this and kind of get into the details of why we think there is a problem and what we think is causing it, I think it might be helpful to share a couple definitions from a recent National Academies report on this topic that tries to distinguish a little bit between two aspects of reliability of science. And so they set up the terms reproducibility versus replicability or replication. Reproducibility is a narrower look at this. It's just obtaining consistent computational results using the same input data, code, conditions of analysis. And essentially, this is what I think a lot of scientists think of as just good quality assurance, quality control, to make sure that the actual analyses of your data that you're doing are documented well enough that they can be repeated and that they give you the same results when you repeat them. That's a lot more narrower than the bigger issue, which is replicability or replication. And the idea of replicability is obtaining consistent results across studies, which doesn't mean exactly the same results, but reasonably consistent results across studies that are aimed at answering the same scientific question, each of which has obtained its own data. Right, and this is an important question, right? If we care about the reliability of our scientific findings, and we believe, as many of us do, that what we're trying to do is trying to find out generalizable information about exposure-disease relationships, then that information should hold up when we repeat those studies or do similar studies in different populations at different places at different times with similar exposures. Okay, so why do we think there's a problem? Well, there's empirical results across a number of fields, not necessarily environmental epidemiology per se, but it doesn't appear that any field is really immune for this problem. For example, there's the psychology example from the Open Science Collaboration, where an explicit effort to try to repeat some of the most famous findings from the field yielded only 39% of the 100 findings that they selected could actually be replicated with similar results. And on average, the effect size in these studies decreased by about 50% upon replication. This is not unique to observational sciences or to psychology. Bayer and Amgen actually have undertaken their own replication efforts, mostly with biochemical studies in the lab, and found that they could only replicate less than 25% of published findings, again, taken from high impact journals or potential drug targets where they thought the published evidence was promising in terms of something they could potentially commercialize. There are also examples from observational health studies that are in epidemiology and closer to what we do in environmental epi. For example, Dumas-Mallet published in 2016 a review of 385 meta-analysis studies in psychiatry, neurology, and somatic diseases, and found that less than half were consistent with findings from initial publications. Again, with larger effect sizes in the initial publications than were found in the meta-analyses. A more recent example from COVID, hydroxychloroquine treatment was associated in one early observational study with a 66% reduction in COVID-19 mortality. This is a Michigan study early last year, relatively early in the pandemic. But then, this kicked off and helped kick off dozens of randomized clinical trials. And now a year later, looking back at all those, meta-analysis recently found that there was actually on average an 11% increase in mortality among those given hydroxychloroquine compared to the randomly assigned controls. Okay, so why is this happening, and why do statisticians actually expect it to happen? Well, there's a couple key points to understand, summarized here, and we'll get into detail in these, but the most important thing to understand is that statistically significant does not mean true, right? And I think, there's a tendency to want to think, oh, well, it's published, it's peer-reviewed, it's statistically significant, that must be real, but that's not necessarily the case. P-values are actually probability measures that assume there is no association between exposure and disease. Additional calculations are actually required if you want to estimate the probability that there is no association. And this is a sort of classic misinterpretation of p-values that people have. They think it somehow is an indication of the probability that there's an association or no association. Exploratory secondary analyses with low statistical power are less likely to be replicable than primary analyses that are well powered. Publication bias and other selective reporting decreases replicability, and this is probably the one you've heard about as a potential explanation, partly because there's some famous papers talking about this. It's also one of the aspects that's pretty easy to understand. However, publication bias doesn't necessarily explain the crisis, and in fact, it's not necessary to explain the crisis. When you look at the probability calculations, there are other factors involved that may be much more important. Most real solutions for replicability have trade-offs, mainly including decreased detection of innovative associations. So if we actually implement some potential solutions, which wouldn't be too hard to do, the trade-off is that we might actually be more inclined to miss some real associations that then don't meet our more stringent thresholds for declaring they're statistically significant. I think the most important thing I would say, and this is my, my opinion, and what I try to teach my students is that I say, it's good to have a philosophy of replication before belief. You should rarely and perhaps never, make a serious decision based on only one study on a topic. So statistically significant does not equal true. Let's delve into that a little more. So what we're talking about here is that traditionally associations with a p-value of less than 0.05 are described as statistically significant, which is really shorthand for saying we reject the null hypothesis that there's no association between, say, exposure and disease. But sometimes we're wrong about that conclusion, about rejecting the null hypothesis. And just as a reminder, if you ever took a statistics class, you probably talked about type 1 and type 2 errors. Those are the errors describing the times when we're wrong about that conclusion that we're drawing from our significance declaration or hypothesis test. So again, what is a p-value? The p-value, a good definition is it's actually the probability of observing an association at least as extreme as in the study sample, given that there is no effect in the population that our study sample comes from. It's not the probability of there being or not being an effect. If the p-value is low, our supposition is that there is no, or a supposition that there is no effect in the population is unlikely to be correct. And so this is actually a very sort of elaborate logical construction that logicians call contrapositive logic, and it's a form of inductive reasoning. And so we're putting together sort of a supposition, collecting evidence that if it's strong enough in opposition to that supposition, we reject the supposition. Okay, so I think one of the key insights, and this actually goes back quite a ways, the 1980s, and I believe statisticians may have pointed this out previously, but this is a very nice readable paper by Browner and Newman that kind of explains the problem pretty clearly and concisely in terms that epidemiologists will be familiar with. The idea here is that every time we do an association study in epidemiology, and this is not unique to epidemiology, this is really any scientific study that uses significance testing or hypothesis testing, we can consider that significance test as an imperfect diagnostic test. So, for example, if we're using a case control study or a cohort study, right, to make inferences about the target population from which those participants were recruited from or volunteered from, we're going to declare an association, sometimes statistically significant, by comparing the p-value to alpha, which is by convention 0.05, or by using a confidence interval, which is also based on the same alpha, right? We get 95% confidence intervals, again, from this same value of 0.05 for alpha. And so those two methods will give you sort of equivalent results for declaring statistical significance or not. And I'm just suggesting some notation here of T plus for the situation in which we've declared an association statistically significant, because our p-value or confidence interval would suggest it's not compatible with the null hypothesis, so no association. Okay, but again, remembering that we can be wrong about this conclusion and that the association may or may not actually exist in the target population that our sample came from, we're going to need a different notation to actually indicate whether there's a true exposure disease association in that population. So I'll use D plus for that. And there's a reason I'm using T plus or D plus. People who have studied epidemiology and diagnostic testing may have seen this notation before, and it's leading us to actually talking about the positive predictive value, a well-known measure of the reliability of diagnostic tests. Positive predictive value for hypothesis tests is just the probability that there really is a true association in the population, given that we see a statistically significant result in our study. Right, written as a conditional probability, it's just the probability of D plus given T plus here. Okay, well, once we write it this way, it becomes very clear that we can just again relate that positive predictive value to the sensitivity and specificity of our hypothesis tests. And so this notation, this formula should look vaguely familiar because it is exactly the same formula we use to relate positive predictive value to sensitivity and specificity. But in the context of hypothesis testing, our sensitivity of the study is actually literally the statistical power of the study. The specificity is 1 minus alpha. So alpha is 1 minus the specificity of the study. And then we also need a third parameter to compute the positive predictive value, which is the prevalence. And in this context of hypothesis testing, the prevalence is just the prevalence of true associations among all those that are tested. In the literature, people sometimes refer to this as the prior probability of the association or the hypothesis, or the prior odds, which is closely related. Prior odds is just the prevalence divided by 1 minus the prevalence. Okay, so how reliable is a statistically significant result? Well, then we can see from the formula on the previous slide, it just depends on those three parameters: the prevalence of those true associations among all the ones we test, the statistical power of each test, and alpha. So these are actually hard to get a hold of, the exact values for the literature as a whole, but I think informative is to consider the one field that I know of where it's mandatory legally to pre-register your study hypotheses. And this allows us to actually know what the denominator is for all those things that are tested, what proportion are actually true. And so as a surrogate for that parameter, if you use what we have from clinical trials, where we know exactly, all the drugs that people thought, okay, let's give this a try, put it through the whole series of clinical trials to see what happens and see if we can get FDA approval, which here is I take to mean, it really has an effect. Then only actually pretty consistently about 10% or less of those investigational drugs, which remember were selected because there was some indication already from a study or a test or literature that they might be promising candidates. That among those, only about 10% actually get FDA approval. So if we think this is meaningful, which I do as a potential surrogate for the prevalence in hypothesis testing in general, then put that number in 0.096 along with a high value of power. So this would be just an example. Say, okay, if we're considering well-powered studies, which are considered, when you have 80 or 90% power above, and a typical value of 0.05 for alpha, plug in those values to the PPV formula, and you see that actually we have a positive predictive value of only 66%. Again, is to say that given that we have a study that's done with this kind of prevalence, power, and alpha, if we find statistical significance, we would only expect, based on that we'd be correct about 66% of the time that actually isn't going to indicate a true association. Now, in reality, I think that 90% power, if you're talking about fields as a whole, is probably unrealistically high. Secondary aims and post hoc analyses in particular are often underpowered. So if we use 50% power instead of 90%, and the same prevalence and same value of alpha, we get about 52% positive predictive value. And you might think, well, 50% power, that's pretty bad, but that's actually an estimate of average power for all the published medical literature. Going back to Stern and Smith in 2001. Some more recent estimates of average power are even lower. Dumas Mele suggested that 20% might be more realistic for average power if you include, all of the tests and confidence intervals and p-values computed in papers that are published. Now, I add also an example here with alpha equals 0.2 to this slide, because that's actually the motivating example for me getting into this whole area of research and writing about this topic. Some years ago at an environmental epidemiology conference, I saw somebody present results where they explicitly were doing a secondary analysis, and they were worried it was going to be underpowered. And so what they had been taught to do in that situation is to use a more relaxed value, a higher value of alpha. And so in fact, they used 0.2 for alpha. And in my mind, that's exactly the wrong thing to do, because if you combine that higher value of alpha with low power and low prevalence, you've got really awful positive predictive value down to 21%. So you can see here, it's not too hard actually to think that there might be a problem even without bias. All these calculations, the formula I showed on the previous slide, assumed absolutely no bias from any problems, confounding, from selective reporting, from data dredging. And as Leonidas had pointed out, accounting for that potential bias pushes down the PPV even further, and arguably likely less than 50% in most situations. Okay, so we used this 9.6% prevalence from clinical trials as sort of a starting point for thinking about what might be realistic sort of positive predictive values for science. But I think that's actually pretty optimistic, maybe overly optimistic for observational studies. We have to remember that observational studies that we do in epidemiology have much lower costs compared to randomized clinical trials. And also in observational studies, we can actually investigate many risk factors at once, most of which are not necessarily expected to have true effects. For example, we might measure several or dozens of different chemicals using exposure biomarkers, or increasingly in recent literature, thousands of genes or proteins as potential responses to exposures. So if we start thinking about maybe lower values of prevalence here, and probably, even for well-powered design, 80% is a pretty common acceptable power for study designs. We use 80% power, alpha equals 0.05, and again with 1/10 for the prevalence, which is about 10%, which is what we started with roughly, we'd see a positive predictive value of 64%. But the PV very quickly drops off as our prevalence decreases. So if we really think, for example, we're measuring many things and only 1 in 100 of those are likely to actually be a true association in the population, then our positive predictive value, even if every one of those is well powered, is going to be only 14%, which is telling us again, only 14% of the time are statistically significant results actually going to indicate a true association. If we're really measuring thousands of things, like thousands of genes, and only expect 1 or 2 to actually be associated with the exposure, then we're looking at positive predictive value that's really miserable, down at about 2%. Now, the good news with this this multiple comparisons issue is that we can protect against it. There's well-known statistical methods for doing so. Bonferroni correction is one of the oldest and most famous and easiest to employ. You just take, for example, alpha divided, the alpha you would normally take, like 0.05, divided by the number of tests. There are other methods. False discovery rate corrections are kind of more popular these days. They're a little less conservative, but they also do a pretty good job about protecting your positive predictive value from dropping based on low prevalence, just solely to sort of increasing the number of tests. Okay, this is just a plot of the graph. I'm sorry, of the equation from a couple slides back for the positive predictive value as a function of prevalence and power given alpha of 0.05. And if you start to look at this, you can see why this sort of keeps me up and other people up at night. I think there are some people who argue that we should assume that the prevalence of our true associations is pretty high, maybe above 50%, because we're smart people and we think deeply about this stuff and we're almost always right. I've heard that argument. I'm not in that camp. I think it's more likely, even though we're well-intentioned, and I like to think a lot of my colleagues and I are smart, that more often than not, we're probably looking at things that may not necessarily actually be associated, particularly when we're doing lots of analyses in the same paper, which we often do because we have these data, we want to take advantage of them, and it's not unreasonable to look at maybe secondary aims and secondary hypotheses that weren't necessarily the main thing we set out to do. And so I worry that we're really more in this range of prevalence below 20–25%, and possibly very well below. And you see that in that range on this plot, the left side of the plot, it's very easy to get down into positive predictive values that are less than 60–50%, even without, again, any bias entering into the situation. Now, unfortunately, bias does occur in most fields, including epidemiology, and there's some important reasons for that. Some of them are avoidable, some are less easily avoided. So falsification of results is kind of the most famous version of this. Hopefully, it's actually very rare, but it has happened, and people have gotten caught doing this, and so it's real. Hopefully rare, though. I think more common problems are probably data dredging, also referred to as p-hacking. And this really includes a lot of behaviors that some people don't even realize are problematic. Things like changing the exposure metric or the outcome disease definition to obtain until you obtain statistical significance, excluding some results until you obtain statistical significance, or keep running different models, choosing different statistical models until you find a statistically significant effect. One really easy way to do this, if you're unethical, is to just do a whole lot of post hoc subgroup analyses. And you see this or suspect this sometimes when you see somebody report in paper that they didn't see for their primary hypothesis any association between exposure and disease. And so they kept looking in subgroups, and they finally found something in 30 to 39-year-old women. And so, then they say, aha, statistically significant. But again, it's very easy to generate something that's statistically significant if you keep looking until you find it. Statistical bias from selective reporting of results is also a potential problem. Again, well known, publication bias and the file drawer problem, that people are less excited about writing up and submitting, and journals are potentially less excited about publishing null results that don't show exposure disease associations. And of course, this creates bias, right, and reduces the probability that an actual reported statistical significant finding is actually true. Stepwise regression, other types of variable selection, although popular, can also contribute to this problem. If you think back, several versions of stepwise regression are dependent on kicking variables out until you find things that are statistically significant, right? So again, you're sort of futzing with the model until you achieve statistical significance. Setting multiple models and reporting the best results is problematic, particularly if you define the best based on which ones give you statistical significance, right? So anything sort of aimed at finding statistical significance can contribute to these types of bias. But it doesn't necessarily have to be bad behavior, whether it's unintentional or intentional, that can lead to bias. There are a lot of biases that are just difficult to avoid in observational study designs. Confounding, selection bias, and other there's limitations that are inherent to observational studies. We do have the ability to avoid or at least limit and control for many of these things. And so good study designs do that to the best of their ability, but it's hard to ensure that there's no remaining bias in these studies. How much does bias contribute to false findings? Well, it depends on the proportion of null effects reported as significant due to bias. And this is really an unknowable parameter, but Unitas, who famously published one of the most cited papers of the last 20 years, and certainly the most famous paper on the replication crisis, added it explicitly to modified the equation I showed you earlier to incorporate this bias parameter, and then proposed some reasonable values, which you might take as hypothetical values for this bias parameter, suggesting 10 to 20% for studies that use standardized or statistical models that are selected a priori before the data are collected, 30% for more typical epidemiologic studies where some methods are chosen along the way, and then 80% for exploratory analyses using data dredging and or lack of adjustment for multiple comparisons. All right, and you can see the same parameters here basically that I have in my equation. They're expressed a little differently, but 1 minus beta is just the power, the statistical power. R is the prior odds of the study, again, which is just a slightly different version of the prevalence parameter. And then the U is the bias parameter. And again, he's thinking about, alpha is 0.05, which is the most common value of alpha to use. And you can see, he argues, again, pretty easy to see, even if you assume high power, like in the first 3 rows of this table, that it's not too hard to get into situations, even with just moderate bias, and still relatively high prevalence values that exceed the values I've suggested might be more reasonable. You can start to get down to pretty low positive predictive values very quickly. So one of the billion-dollar questions here, is environmental epidemiology different than other fields? Everything I've kind of suggested here, I think, is really relevant to all fields of study. There's some things that are a little bit unique to epidemiology, but I think environmental epidemiology is unlikely to be really much different than other observational sciences in regards to our potential exposure to this problem. So prevalence and power for the field as a whole are unknown and perhaps unknowable. I should really be clear that those estimates of 50% and 20% from those other papers, although they involve some empirical review, are also, partly guesswork. And so we don't have good handle on what these things are. Prevalence, we would need mandatory pre-registration of all hypothesis tests in order to really have the denominator to get an accurate value for Prev. And so that's also, really hard to know, but we have some hints and ideas that I've suggested. Although many topics have been investigated in more than one study in environmental epidemiology, which is one thing I think we do pretty well. I think, at least the way I was trained, I think it was understood that you wouldn't put a lot of trust in any one study, that you'd want to see things replicated before you start to really believe them. And so we do have a culture of trying to look at the same exposure disease relationship in more than one study and more than one population, which is good. But I haven't seen yet any large-scale replication analyses attempted for our field, like have been done for psychology or other fields. I think one thing we have going for us in environmental epidemiology is that biomarker measurements are relatively expensive, and so we usually select them a priori because we have to, because we only have limited budgets, and so we have to be sort of thoughtful and choosy about what exposures we actually measure. That is starting to change though with exposomics, and I think as larger scale, multiple biomarker kind of studies, exposomic type studies get done, we'll see more of this problem of potentially, fewer sort of exposures selected based on hypotheses and more just done because you can measure them. Air pollution studies often examine multiple pollutants, multiple time lags, multiple outcome measures with hundreds or thousands even of analyses in the same paper. And so this would support the idea that maybe there's some multiple comparisons problems in a lot of that literature. And so it's not typical, in fact, for people to adjust formally for multiple comparisons in those papers. So I would certainly keep that in mind as you review those kind of papers and think about the number of tests versus the number of statistically significant findings. Major findings, though, on acute air pollution, hospitalization, and mortality have been replicated many times, and really, are very persist through systematic reviews. People who've really looked at the literature as a whole, considered things like publication bias, are pretty well convinced that those are real effects. And so I don't want to paint too dark a picture here. I think there's certainly some things that hold up and seem to be reliable. NIH has proposed some solutions to this, which I want to talk about a little bit, because there was a lot of excitement around the idea that they were going to step in and try to fix this problem back in 2014. Francis Collins, the director of NIH at that time, wrote this paper in Nature talking about all the things they were going to do, and they did them. They put these into place in 2016. I think, though, looking at actually what the new guidelines are, how they're employed, it's not entirely clear to me that these will address the three key parameters in determining the reproducibility, the positive predictive value of studies. I should say the replicability, not the reproducibility. So these included things like requiring those writing grants and reviewing grants to pay attention to the scientific premise and thinking about, the actual prior research being cited by the application to support, doing more work in that area. In theory, that should increase somewhat the prevalence if it's employed well. It's less clear if it's actually having that effect, though. Scientific rigor, strict application of the scientific method, full transparency in reporting details so that others may produce findings. So this is really more focused on the reproducibility, right? That ensuring that you actually have transparency, that the methods can be repeated, and so I think, again, it's sort of limited in how much that contributes, as it doesn't directly affect those three parameters. Consideration of relevant biological variables, sex, age, weight as factors. That's kind of an interesting one. I'll talk a little more about my thoughts on that on the next slide. And then authentication of key biological and chemical resources, right? Make sure the cell lines, the antibodies you're using are what you think they are, and that they're not contaminated. Again, a lot of this is really more focused on QA, QC and kind of classic considerations. I don't know that there's a lot here that will actually decrease bias, increase prevalence, or do other things that would actually change the PPV calculation. Some trends in epidemiology that might affect this, reducing positive predictive value, I think, are things like the fact that we're now doing more and more exposure mixtures, multiple exposure measures, the omics and big data with measuring many, many things, which leads to lots of comparisons, often exploratory, right? So even if we're doing formal adjustment for multiple comparisons, which helps, we still have lower prevalence for any one of those prior odds for the studies or prior probabilities from actually for each individual thing being measured actually having a true association. The increased study of potential sex and age and race differences is interesting. There's an argument to be made that this is important and worthwhile. However, if there are real differences across any of those characteristics. However, the risk here is that this actually leads to more comparisons, because now we're doing all those sort of subgroup analyses that I warned about earlier. Each one of those is done with a smaller sample size. We're dividing our study sample size in half now to look separately at each sex. We're dividing it into smaller numbers for each age group, each race group. And so that will lead to lower power for looking at exposure disease relationships within each of those groups. And again, that creates a greater risk of sort of false statistically significant findings. On the plus side, we have some trends that might increase PPV. Journals seem to be more open to publishing null findings, reducing publication bias. And I think epi journals have actually had a pretty good track record on this going back quite some time, at least for large, well-powered null studies. But I think, increasingly they're actually being more explicit in their guidelines about discouraging reviewers from using this as a reason to sort of recommend rejection of paper, and trying to encourage people to actually submit null findings. So I think that's a positive development. Grant and manuscript reviewers are paying more attention to adjustment for multiple comparisons. I've seen this in the study sections I've sat on for sure, and putting secondary analyses in context. One interesting development, and this is not for epidemiology per se, but in science as a whole, I've seen there's an estimate that journal article retractions have actually increased about 40-fold over the last decade or two, which is a huge increase. And I think you could take this either way. One might look at that and say, well, that's increased evidence that people are behaving badly and doing p-hacking or other data, falsification that needs to be then retracted. I actually take a more optimistic view on this. I think there's been some of that happening all along, but that now people are becoming more aware of it and that people are getting caught more for doing it. And that's why the journal article retractions are increasing, but it's just my supposition. Okay, so I'm going to kind of wrap up with a couple of things. One is just a nice quote from Dickens that I think fairly expresses how I feel about doing science in the modern age. It was the best of times, it was the worst of times. It was the age of wisdom, the age of foolishness. It was the epoch of belief, it was the epoch of incredulity. It was the season of light, the season of darkness, the spring of hope, the winter of despair. We had everything before us, we had nothing before us. And I think this nicely captures how I feel, because we have this now tremendous ability to measure so many things. Big data is upon us. We have many, many more public data sources, computerized data sources than we ever had before. We can now, more easily include many, many measurements and variables in our studies. And so this is incredibly exciting as a scientist to see this, but it also comes with an incredible moral hazard and incredible risk, right, of generating false positive results. And so I do worry about the implications of this for the reliability of our findings going forward. So just so we don't end on too dark a note, I'm going to finish on sort of a list of suggestions that I and others have offered as what we can do as scientists or as consumers of science to think about how to remedy the situation. One is that we can increase the Prev parameter, right? And how do you do that? Well, you do hypothesis-driven research, right? And if you're a user of a science or a reviewer of science, then you give those studies more weight when you're reviewing them, right? By recognizing that if you have a study that was set out with a specific goal of addressing one exposure-disease relationship and saw an association, that's more likely to have a higher prevalence than, say, a study that looked at 50 different associations and then found one that was statistically significant. Another thing you can do is increase power, right? Larger sample sizes and or more efficient study designs. And I think there, honestly has not been enough attention to power. I think epidemiologists do think about it. I see it in every grant application I review on the epidemiology side, but not necessarily in toxicology or in other fields. But even so, the grants I review, typically, and the ones I write, typically we only do power calculations for our primary hypotheses. So I think we need to think more about, power for these secondary hypotheses and what's really practical and worthwhile for doing there. One can also decrease alpha. This is an idea that was actually been signed on to by hundreds of statisticians and other scientists now, in a nice paper, Benjamin, which has hundreds of authors who signed on to the suggestion of perhaps making 0.005 a more standard default value for alpha rather than 0.05. 0.05 is not, it's just an arbitrary value. It was chosen by Fisher almost 100 years ago now, I think over 100 years ago, as an example of a value that might be reasonable to use. And it caught on mostly because he put it in his textbook. There's not a particular reason we should stick with 0.05. This is an interesting idea. It has the downside, though, of then making it more difficult to find associations, right? So you have to either increase the sample size dramatically for your study to maintain power, or potentially then you face the risk of actually missing real associations. Formal adjustment for multiple comparisons is important, I think, and useful. And there's been some controversy about this in epidemiology in the past, including famous article or two by Rothman saying this is unnecessary, that everything we do is hypothesis generating in epidemiology. But I disagree with that. I think it's worthwhile to kind of do this, particularly as we move into testing, hundreds or thousands of things in the same papers. We can decrease bias by avoiding data dredging and p-hacking, and this is why it's really important to educate students, even in introductory statistics courses, on this issue. And I give a similar version of this lecture in my intro biostats course for our graduate students. Publish all results, not preferentially reporting only the statistically significant ones. Some people have suggested pre-registration of epidemiologic hypotheses might be useful for enforcing this. More cautious interpretation, I think, is probably the most practical thing you can do as both, again, a scientist and, more importantly, as a reviewer and a reader of science. Emphasize effect size estimation rather than hypothesis testing if you're writing papers, and pay more attention to effect size and confidence intervals as a reader than to just the statistical significance. Replication before belief, as I've mentioned before. And, really, I would say if you're a user of science, pay a lot more attention to reviews and meta-analyses than to any one individual study, because that's where people really attempt to really kind of put it all together and say, what does the literature as a whole say? Which isn't to say that that's perfect. Again, publication bias can affect those, but there are tools for evaluating publication bias in meta-analyses, and increasingly those are being employed. Finally, identify exploratory or secondary analyses, either as a producer of science or as a reviewer, and expect lower positive predictive value for those analyses. And that is my talk.
Thank you so much, Scott. It was an excellent talk. This time I would encourage our audience to enter your questions in the question box. You can type them and our panelists will read them to Scott.
Well, we wait for folks to jump in. I'm Igor Burstin. I'm one of the people responsible for this affair. So wonderful talk. Thank you very much.
Thank you.
I'd like to share with you one of my worries that relates to recommendation to increase sample size and see what you think about it. When we have very large sample size, all the imperfections in our study are amplified. All the good things are amplified if there's true association, but all the imperfections, a tiny source of bias, selection bias, confounding, or bias from measurement error might not manifest itself to a measurable degree in a smallish data set. But once you ratchet up to infinity, it really begins to drive the answer. Paul Gustafson talked about it. So how do you balance this advice of huge studies which are guaranteed to give you tiny p-values? We all know that in practice, to the point where we ignore p-values in a really massive data set in practice. So where do you think the balance lies?
Yeah, it's a great question. I mean, I guess my view is slightly different. I don't know that I'd say that the bias from confounding or other selection bias is amplified by large sample sizes. It's more that the random error is diminished, right? So relatively speaking, confounding, selection bias become relatively more important. It's not that
right. It just it drives it. It just
random error becomes smaller, right? So I guess though I do agree. It becomes an issue again. I think Tim Lash, very persuasively, and others write about how one solution to this is to move away from this binary thinking about statistically significant versus non-statistically significant, which I think is harder to do in practice than Tim might suggest. He said, we'll just stop thinking about statistical significance, but I think it's so ingrained in the way we do business, and it's popular because it's a convenient way to reduce, complex results to, is there an association or is there not association? But I do fundamentally agree that it's more important to really think about the effect size and the confidence interval around that effect size. Tim Lash has proposed some ways to sort of fix up the confidence interval to try to account for those potential impacts of confounding or selection bias to get a more sort of realistic picture of what a realistic range of effect sizes are. But I think this is something the causal inference people really have right, is that they say, well, don't focus on just yes or no, it's associated. Focus on, what are the actual, what would be the change in health status? How many cancers would we avert if we reduce that exposure? And I think that kind of thinking is useful in a couple ways. One is that it actually helps, quite apart from the statistical significance issue, just helps you focus on, what you actually can do as an intervention, and would that intervention have a small or close to null effect, or would it be a large effect? And how certain are we about the likely impacts of that? And I know that's not a very satisfying answer, but I
No,
think that's
it's a fantastic answer. Thank you.
rather than the, you know, and whether the effect size is near null or whether it's, you know, something more substantial where intervening would actually have a big effect.
Yeah, and your comments definitely dovetail with the question of what is it for? And, you know, Bradford Hill talked about it a long time ago. So like we care more about risk of Armageddon rather than risk of stub toe and their counts. So thank you. This is definitely very helpful. Maybe I'll ask David Miller to lead with the next question, because I haven't been reading questions coming from the audience, talking to
Sure, a few have come in, so I'll ask this one. In recent years, there have been about 6 meta-analyses on the epidemiological studies on glyphosate, with about half reporting a significant association, confidence interval not including 1, and half reporting a non-significant association. How should a non-epidemiologist make sense of these results?
Yeah, that's a great question. I'm not familiar with that literature. I have to admit, I'm not following, you know, I've heard a few things, read 1 or 2 things about the glyphosate literature, but I have not read any of those meta-analyses, so I'm not in a good position to comment. But I think, you know, that is a situation, again, where, you know, the devil's in the details. And I think that's true of, you know, any systematic review and meta-analysis. It's probably very difficult as a non-epidemiologist to say, who do I trust in that situation, or what do I believe here? I would say, though, you know, my best advice, not having read these particular studies, is, you know, I would go into the detail a little bit on, you know, seeing if you can figure out why they're different, right? Because that can be informative. Even if you're not sure which to trust, you can at least perhaps identify, you know, did they include different studies or exclude different studies? Is that why they're coming up with different results? Or are they somehow giving different weights to different studies? You know, we often do weight of evidence qualitatively, but I've seen some people use quantitative weights for meta-analyses, and so that's about the best I can say there. Is sort of, you know, unfortunately you have to sort of get into the details, and it might be helpful to, you know, even if you're not an epidemiologist, to partner or talk with an epidemiologist about helping you review those studies.
Okay, thank you.
Let me jump in with the next question, because another fantastic question from the audience that reads, as a state health agency, we're often asked to do cancer cluster investigations. The question is really, how do you apply what you've presented to those types of analysis? How would you modify how you talk about the results to community members who are really very interested in the result? So talking about how do you talk about small things that are raw?
Yeah, cluster analyses are sort of a classic example of you know, this sort of problem, right? Which is that you sort of go looking for something post hoc, you know, and it's a very challenging one, right? Because it's very compelling to say, yeah, we need to look at this and see if the rates are elevated, but that usually starts with the fact that there's some perception that the rates are elevated before you actually look at the numbers. And so a lot of the issues with sort of multiple comparisons can be applied to thinking about cluster analyses. And there are some papers where people suggest ways to sort of fix up the p-values to count for the fact, for example, you know, if you have a town of size 5,000 and you're looking for a cluster, you know, you can actually consider, well, what are all the, you know, if we applied that to every pocket of 5,000 people in the country, you know, how many different comparisons would that involve? And so it's you know, it's not necessarily a perfect way to fix up the fact that you've sort of inherently got some underlying things you didn't study that went into sort of detecting this cluster, but it's, I think, not an unreasonable approach for getting a sense of whether that's really unusual in the context of, you know, how many people are you studying compared to how many people you could have studied, say, in the US. So that is a technique, and I wish I knew the paper off the top of my head, but I can't remember where I've seen that, but I know I've seen papers that sort of try to account for that in that way.
Okay, thank you.
I don't see another question, but I'll go ahead and go ahead. Is there another one up there?
Yes, there is a question from a member of the audience. It says, great topic. I was intrigued with the discussion on effect size. I've noticed that air pollution studies have huge small sample sizes, millions of subjects, with tiny effects on the order of less than 1.2, depending, what you standardize them to. One could argue that these are small effects and little impact. Alternatively, since many people are impacted, a change regulation possibly would reduce disease in an important way. Any suggestions how to navigate this mess?
Yeah, I'll just say I agree. It's a problem, right? I mean, you have relatively small effect sizes, which, as Igor, you pointed out earlier, right, which we know are more likely to be affected, or caused, say, solely by a bias like confounding or selection bias. On the other hand, we've got huge studies. There's fairly good consistency for some of these outcomes of air pollution that they're in this like sort of 1.05 kind of 1.1 range. And so it's a tough question of what you do with that. I actually would argue, and we're actually designing and about to implement in California one right now, that we should be doing more randomized controlled trials of air pollution interventions, because that is one way to avoid at least the confounding, the selection bias issues, right? That we've got this tremendous body of observational epidemiology suggesting something's going on. Maybe it's time to start moving that now into intervention science. So we actually collaborating with Veronica Vera here at UCI to do a filtration study with randomized classrooms in Los Angeles area. So we're really excited to be doing that, because even though we think there might be reason to expect real benefits based on the observational studies, there is this problem of the small effect sizes, which it's hard to sort of separate out whether that might just be a small confounding or selection bias issue.
Or measurement error.
Or measurement error.
Our bugbear, especially in air pollution.
Yeah.
David, you have a question. Could you maybe you can jump in?
Yeah, actually, I was maybe a follow-on to this one in terms of you talk about kind of doing trials on. I guess, do you have any thoughts about natural experiments in this field? I've heard the Beijing Olympics, for example, they limited, I think, car traffic, a variety of other pollution sources, and then I think they measured reductions in a variety of air pollution ailments or something like that. Any thoughts on that, or how that could be done better, more often, more frequently? Epidemiology do that?
Yeah, and I think we should do those. I'm actually a big fan of natural experiments, and I actually tend to think of our C8 studies on PFAS that we did in West Virginia and Ohio that way, because we had, communities with fairly similar demographics, socioeconomic status, that just by virtue of which were upwind or downwind of the exposure source, the plant that was manufacturing PFOA, happened to end up with, relatively low amounts of PFOA in their water, or very, very high amounts, and then some with water systems with amounts in between. And I think those kind of studies are, relatively robust to some of the issues we've talked about, particularly the confounding issues, I think are much less of a problem in these natural experiments, which isn't to say there isn't, some possibility of confounding, but it's just, I think, a lot less likely an explanation than, situations where we have, like general population exposures where we're studying, where it's often very difficult, for example, with PFAS, to even know what the sources are. So yeah, I think we should be looking for more opportunities with like highly exposed populations that have innate variability due to things that are not related to personal behaviors, that are just by circumstance of exactly where they were relative to the source, for example, or pre-post comparisons like the Beijing Olympics, right, and sort of time comparisons where you have a factor suddenly changing and then changing back, and I think those can be. Again, they don't solve every problem, but they can be tremendously informative, because they really reduce the potential for certain types of bias.
Yeah. Okay. Thanks. Go ahead, Igor. There's one more question.
Yeah, I would like to jump in with an entirely selfish question, if I may. It might be of general interest, and that is the proposal for S-values that Sander Greenland and his colleagues have been proposing as a solution to the cognitive problems of p-values, pretty much all statistics. I don't mean to put you too much on the spot, but if you had a chance to study the issue, would love to hear what your thoughts are as one solution to cognitive in dealing with statistical results.
I have to admit, I have not yet read that paper, so I'm not
Okay.
going to comment
Sorry.
or take a position. But now you've got me intrigued, so I'm going to put that on my list to go read.
So, and then there's a question from the audience. Do you have any thoughts of multiple papers that use the same data set to suggest that different chemicals cause the same set of effects? So
So
many
could you repeat
papers.
that question?
So what are your thoughts on situations where you have many papers that use the same one data set to suggest that different chemicals cause the same set of effects?
Well, that's that would be problematic if you're not mutually adjusting, right? Or acknowledging that there's, some other possible causes. So, if you've got multiple exposures going on the same data set, it's not necessarily problematic if they're not correlated, right? Because, then it's not a confounder, it's not necessarily to adjust for it. But if you have correlated co-exposures, it's not good to sort of present those in separate papers without, some discussion. I will say, in air pollution, it's actually in the literature, it's very common, even though we know we have correlated copollutants, to actually fit separate models that are not adjusted for each one. And we do this actually in some of our own papers in the PFAS literature. We have multiple PFAS. We tend to do it both ways in my research group, where we mutually adjust and then we put them in one at a time. But there are some challenges actually with the mutual adjustment, including Z amplification bias, which is a problem that arises if you have measurement error in every one of those. Methodologists point out sometimes it's worse to mutually adjust. It goes back to the old collinearity problem essentially, but then with measurement error, it makes it even worse. And so there is some debate about the proper way to actually analyze those, but I would think you'd want to acknowledge at least that, you have these correlated co-exposures if they're indeed correlated.
Thank you.
So we are at the top of the hour. So in the interest of everyone's time, I think we should probably stop here. If there are a couple additional questions, and we can communicate them to Scott, and he could potentially answer to you in private for those of you who haven't had the chance to have your questions read here on the webinar. But I wanted to say a big thank you to you, Scott, for your time, for agreeing to do this. We very much appreciate it. Also, thank you to David and Igor Borstein and David Miller, the co-chair of our committee. So thank you for moderating the questions. And a few more things. So again, the webinar was recorded and it will be posted shortly on HESI's Environmental Epidemiology Committee webpage. Just so you are prepared, our next webinar will be in less than a month on November 17th, and it will be presented by Dr. George Maldonado, who is at the University of Minnesota. So the webinar will be at the same time from between 1 and 2 p.m. Eastern Time. Dr. Maldonado's presentation will be about causal reasoning in public health, philosophy, and logic. So we hope you will join us for that too. And finally, if you have any questions, comments, or if you'd like to suggest speakers, please don't hesitate to send me a note. Also, feedback on these webinars is always welcome, so do not hesitate. And with that, we will adjourn this webinar. So thanks everyone again. We appreciate your joining.
Thank you for the invitation.
Thank you, Scott.
Great, thank you. Okay. Okay, great.
Okay, that was fun. Thank you.
Okay, thanks. That was, yeah, really good on that.
I'm sorry you didn't get to ask more of your own questions, David. I know you have dozens.
No, that's fine. I keep those basically just in my back pocket. If there aren't a whole bunch of questions, there were, no, that's great. So we'll be communicating back. I think there are a few extra questions that came up, and there weren't many, maybe an extra 2 or so. I understand Sandrine will get in contact with you if you're willing to kind of give a written answer to some of those.
Yeah, absolutely. Just email them to me. I'd be happy to think about them and give a response.
Yep, great. Okay, thanks very much.
All right.
It was really good. Okay, bye-bye.
Bye-bye.
Let's see.